Welcome to HB Tuner's GM Gen 5 Training Part 11. In this training module, we're going to be taking a look at the injector data characterization that we have to program in our calibration file. So if we're switching our injectors out, we want to be able to go and fix the data. Also understanding how this injector data fits into the direct injection that we have going on for the Gen 5 applications. We're going to have a lot to talk about. Let's jump in so we can check this out. Okay, so let's get started. We're going to be taking a look at working with our fuel injector programming in our Gen 5 applications. Now, the fuel injector programming is something that we want to understand so that we understand how the fuel mass is converted into an injector pulse width. It's going to be quite different in terms of the programming and the flow of how the injector data is going to fit into that conversion compared to the Gen 3, Gen 4 applications where it was a port injection engine. The injectors are actually mounted in the intake manifold and they spray above the intake valve. It's quite different in the direct injection format where we actually have the injector tip in the combustion chamber and it's spraying within a very narrow window of the engine's operation within the Otto cycle. So the way that the injector program is going to go is different, and we definitely want to understand this. So if you're changing your fuel injectors, let's say to Z06 injectors, if you're going from, let's say, an LT1 engine, it's naturally aspirated, putting on a supercharger, turbocharger, and you need more fuel flow, you're going to have to go and upgrade either your camshaft with an overdrive lobe on the cam to overdrive the mechanical pump, changing out the mechanical pump itself, so the high pressure pump on the engine, and or changing the fuel injectors. If you change the fuel injectors for more fuel flow, you do need to program all the tables we're going to be talking about here, specific to the Z06 injector data. So we're going to look at how these tables fit together, how everything's going to work, just getting an understanding of how the programming is going to be within the Gen 5 family. Okay, so the first thing I want to go and outline here, I am working with a 2018 Yukon Denali file. You can open up any Gen 5 file to follow along here. I'm going to go into my engine tab, and in here, we're going to go from our general tab into fuel and then fuel into general. And then under this general tab, we're going to be specifically taking a look at our fuel flow rate, our limits, our offsets, our pulse corrections, and then down here, injector profiles. All of this fits together in order to tell the engine control module how the injector flow is going to be varying based on a wide variety of conditions, such as fuel pressure or the injector tip temperature, where the injector is mounted within the combustion chamber, how hot that's getting. It takes into factor the density of the fuel that's being sprayed out of the injector. A lot of high-level modeling going on here. We definitely wanted to understand how this is all going to work. So the very first thing we're going to be turning our attention to is understanding the first portion of how the fuel mass gets converted into an injector pulse width, and that's based up here around our flow rate. Now, just quickly to backtrack, we have an underlying equation in our Gen 5 and actually all GM, ECM, engine control module programming. That's going to be fuel mass is equal to air mass divided by target air fuel. We've talked about this already in previous training modules. Now, the air mass is coming from the mass airflow sensor or speed density, or a combination of both, which is known as our dynamic airflow. Either case, we can figure out what the air mass being ingested into the engine is going to be at any given time. Knowing the air mass and knowing what the desired target air fuel is going to be, we can then calculate a fuel mass. We would then convert a fuel mass in grams per second into an injector pulse width based on knowing the data that we have programmed here. So we need to know the flow rate, we need to know the offset or the latency of the injector, and then the short pulse width, as we're finding down here, short pulse width adder that accounts for nonlinear behavior of the injector. All of this fits together into giving us a total injector pulse width that we send out to the injector to pulse it, to deliver the fuel mass that we're trying to request through that basic equation that we have going on here. So essentially what we're interested in here is how the fuel mass gets converted into an injector pulse width, how all these tables here fit together. So let's jump in here and take a look at fuel flow rate. Now the fuel flow rate, this is going to be starting to figure out what the base injector pulse width is going to be. So this would be known as our static flow or the slope of the injector operation. So let's actually take a look here at a graphical plot so we can understand what this means and how this is going to fit together. So this is, again, the injector flow rate here is going to give us the base injector pulse width. And then our other tables here are going to be adding on to that to give us a total corrected pulse width, or being able to characterize the injector's response. So taking a look at our graphical plot coming up on screen, we have our left axis, which is going to be based on injector flow, and our bottom axis is going to be based on injector pulse width. We can see here the left axis showing injector flow, we have 5, 100, 150, and 200 pound per hour values or tick marks on our axes. Down below, we have 1 through 7 milliseconds. A millisecond is the frame of time reference when we're talking about how the injector opens and closes to spray the fuel. So everything's always referenced in milliseconds. And we can see we have a bunch of different tick marks there representing different amounts of injector pulse width. Now what we need to take away from this is that the value that we're finding right here in this flow rate value, we can see it's represented here as 118.7 pound per hour. That's telling the engine control module that this is what the injector we have installed is going to flow. This is also in programming language known as the injector slope, or the rise over the run. So let's understand how this is actually going to work. Thanks for checking out our teaser clip. If you want to see the rest of this video and more than 500 hours of current EFI training we have to offer, make sure you click right here. If you want to go and check out more teaser clips from this training course, click here, and you don't want to miss any of the videos we're going to be releasing on this channel, so make sure you subscribe and click here. Thanks for watching, and I'll see you guys later.